We're going to move now into actually solving the Schrodinger equation. This is really the main meat of quantum mechanics. And in order to start tackling the Schrodinger equation, we need to know a little bit about how equations like the Schrodinger equation are solved in general. One of those solution techniques is separation of variables, and that's the solution technique that we're going to be applying repeatedly to the Schrodinger equation. First of all, though, let's talk a little bit about ordinary and partial differential equations. The Schrodinger equation is a partial differential equation, which means it's a good deal more difficult than an ordinary differential equation. But what does that actually mean? First of all, let's talk about ordinary differential equations. What an ordinary differential equation tells you is how specific coordinates change with time. At least that's most applications. So you have something like x as a function of time, y as a function of time, sorry, not y as a function of x, y as a function of time, z as a function of time. For example, the position of a projectile moving through the air could be determined by three functions, x, y, and z. If you're only working in two dimensions, for instance, let me drop the z, but we might have a velocity as well, say vx of t and vy of t. These four coordinates, position in two dimensions and velocity in two dimensions, fully specifies the state of a projectile moving in two dimensions. What an ordinary differential equation might look like to govern the motion of this projectile would be something like the following. dx dt is vx, dy dt is vy. Nothing terribly shocking there. The position coordinates change at a rate of change given by the velocity. While the velocities change, dvx dt is given by, let's say, minus kvx, and dvy dt is minus kv subscript y now, kvy minus g. This tells you that where I got these equations, this is effectively damped frictional motion in the plane xy, where gravity is pulling you down. So in the absence of any velocity, gravity leads to an acceleration in the negative y direction, and the rest of this system evolves accordingly. What that tells you, though, in the end, is the trajectory of the particle. If you launch it as a function of time, tick, 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 as the projectile moves through the air in, say, x, y space. Partial differential equations, on the other hand, PDEs, you have several independent variables. So where in an ordinary differential equation we only had time, and everything was a function of time, in a partial differential equation, what you're trying to solve for will have several independent variables. For example, the electric field, the vector electric field in particular, as a function of x, y, and z. The electric field has a value, both a magnitude and a direction, at every point in space, so x, y, and z potentially vary over the entire universe. Now you know how, excuse me, you know a few equations that pertain to the electric field that maybe you could use to solve to determine what the electric field is. One of these is Gauss's law, which we usually give an integral form. The integral of the electric field dotted with an area vector over a closed surface is equal to the charge enclosed by that surface over epsilon naught. Now hopefully you also know there is a differential form for Gauss's law, and it usually is written like this. This upside down delta is read as del, so you could say this is del dot E, and this is a vector differential operator. I'm going to skip the details of this because this is all electromagnetism, and if you go on to take advanced electromagnetism courses, you will learn about this in excruciating detail. Perhaps suffice to say here that most of the time when we're trying to solve equations like this, we don't work with the electric field, we work with the potential, let's call that V, and this system of equations here, if you treat the electric field as minus the gradient of the potential, gives you this equation gives you the Laplace equation. Del squared v equals rho over epsilon naught. What that actually writes out to, if you go through all of the vector algebra, is the second derivative of v with respect to x plus the second derivative of v with respect to y plus the second derivative of v with respect to z, and I've left off all my squareds in the denominator here, is equal to rho over epsilon naught. This is a partial differential equation, and if we had some machinery for solving partial differential equations, we would be able to determine the potential at every point in space. And that would then allow us to determine the electric field at every point in space. This is just an example. Hopefully you're familiar with some of the terms I'm using here. The main solution technique that is used for partial differential equations is separation of variables. And separation of variables is fundamentally a guess. Suppose we want to find some function. In the case of electromagnetism, it's the potential x, y, and z. The potential is a function of x, y, and z. Let's make a guess that v of x, y, and z can be written as x of x times y of y times z of z. So instead of having one function of three variables, we have the product of three functions of one variable each. Does this guess work? Well, it's astonishing how often this guess actually does work. This is a very restrictive sort of thing, but under many realistic circumstances, this actually tells you a lot about the solution. For example, the wave equation. The wave equation is what you get mathematically if you think about, say, having a string stretched between two solid objects. Now, under those circumstances, if you zoom in on, if you say, pluck the string, you know it's going to vibrate up and down. Mathematically speaking, if you zoom in on a portion of that string, say it looks like this, you know the center of this string is going to be accelerating downwards. And the reason it's going to accelerate downwards is because there is tension in the string, and the tension force pulls that direction on that side and that direction on that side. So it's being pulled to the right and pulled to the left, and the net force then ends up being in the downward direction. If the string curved the other direction, you would have effectively a net force pulling up and to the right, and a net force pulling up into, or a force pulling up into the right, a force pulling up into the left, and your net force would be up. This tells you about forces in terms of curvatures, and that thought leads directly to the wave equation. The acceleration, as a result of the force, is related to the curvature of the string. And how we express that mathematically is with derivatives. The acceleration is the second derivative of the position. So if we have the position of this string is u as a function of position and time, then the acceleration of the string at a given point and at a given time is going to be equal to some constant, traditionally written c squared, times the curvature, which is the second derivative of u with respect to x. Again, u being a function of position and time. So this is the wave equation. I should probably put a box around this because the wave equation shows up a lot in physics. This is an important one to know. But let's proceed with separation of variables. U, as a function of position and time, is going to be x, a function of, not time, x a function of position, and t a function of time. So capital X and capital T are functions of a single variable each, and their product is what we're guessing will reproduce the behavior of u. So if I substitute this u into this equation, what I end up with is the second derivative of x, t of t, with respect to time, equals c squared times the second derivative of x, t of t, with respect to position. So this hasn't really gotten us anywhere yet, but what you notice here is we have derivatives with respect to time, and then we have this function of position. since these are partial derivatives, they're derivatives taken with everything else other than the variable that you're concerned with held constant, which means this part here, which is only a function of position, can be treated as a constant and taken outside of the derivative. The same sort of thing happens here. We have second derivatives, partial second derivatives with respect to position, and here we have only a function of time, effectively a constant for this partial derivative, which means we can pull things out. And what we've got then is capital X. I'm going to drop the parentheses x because you know capital X is a function of lowercase x. So you've got big X, second partial derivative with respect to time of big T equals c squared big T, second partial derivative of big X with respect to x. That's nice because you can see we're starting to actually be able to pull x and t out here. And the next step is to divide both sides of this equation by xt, by basically dividing through by u. In order for this to work, we need to know that our solution is non-trivial, meaning if x and t are everywhere 0, dividing through by this will do bad things to this equation. But what you're left with after you divide by this is 1 over t, second partial of t, big T with respect to little t, and c squared 1 over big X, second partial of big X with respect to little x. This is fully separated. What that means is that the left-hand side here is a function only of t. And the right-hand side is a function only of x. That's very interesting. Suppose I write this function of t as, say, f of t. This part, let's call that g of x. I have two different functions of t and x. Normally you would say, oh, I have f of t and I have g of x, and I know what those forms are. I could, in principle, solve for t as a function of x. But that isn't what you're going to do, and the reason that's not the case is that this is a partial differential equation. Both x and t are independent variables. All of this analysis, in order for separation of variables to work, must hold at every point in space, at every x and at every time. So suppose this relationship held for a certain value of t and for a certain value of x. I ought to be able to change x and have the relationship still hold. So if I change x without changing t, the left-hand side of the equation isn't changing. If changing x led to a change in g of x, then my relationship wouldn't hold anymore. So effectively what this means is that g of x is a constant. In order for this relationship to hold, both f of t and g of x have to be constant. Essentially, what this is saying in the context of the partial differential equation is that if we look at the x part here, when I change the position, any change in the second derivative of the position function is mimicked by this 1 over x, such that the overall function ends up being a constant. That's nice, because that means I actually have two separate equations. F of t is a constant and g of x is a constant. What these equations actually look like: this was my f of x, and this was my f of t, and this was my g of x. That constant, which I've called a here, and the notation is arbitrary, though you can in principle save yourself some time by thinking ahead and figuring out what might be a reasonable value for a. What's especially nice about these is that this equation is now only an ordinary differential equation. Since big T is only a function of little t, we just have a function of a single variable. We only have a single variable here. We don't need to worry about what variables are being held constant and what variables aren't being held constant. So we can write this as total derivative with d instead of partial derivative with the partial derivative symbol. So we've reduced our partial differential equation into two ordinary differential equations. This is wonderful. And we can rearrange these things to make them a little more recognizable. You've got d squared t dt squared equals a t, and c squared d squared big X d little x squared equals a times big X, multiplying through by big T in this equation and big X in this equation. And these are equations that you should know how to solve. If not, you can go back to your ordinary differential equations books, and solution to ordinary differential equations like this are very commonly studied. In this case, we're taking the second derivative of something and we're getting the something back with a constant out front. Anytime you take the derivative of something and get itself or itself times a constant, you should think exponentials. And in this case, the solution is t equals e to the square root of a times time. If you take the second derivative of this, you'll get two square roots of a factors that come down, e times e to the root at, which is just big T. You can, in principle, also have a normalization constant out front. And you end up with the same sort of thing for x. Big X is going to be e to the square root of a over c x, with, again, in principle, a normalization constant out front. What that means is, if I move things up a little bit, get myself some space, u of x and t, what we originally wanted to find, is now going to be the product of these two functions. So I have a normalization constant in front, then I have e times root a t, and e times root a over c x. Now, if this doesn't look like a wave, and that surprises you because I told you this was the wave equation, it's because we have, in principle, some freedom for what we want to choose for our normalization constant and for what we want to choose for our separation constant, this constant a. And the value of that constant will, in principle, be determined by the boundary conditions. A and a are determined by boundary conditions. The consideration of boundary conditions and initial conditions in partial differential equations is subtle, and I don't have a lot of time to fully explain it here. But if what you're concerned with is why this doesn't look like a wave equation, what actually happens when you plug in to your initial conditions and your boundary conditions to find your normalization constants and your actual value for the separation constant, you'll find that a is complex. And when you substitute in the complex value for a into these expressions, you'll end up with e to the I omega t sort of behavior, which is going to give you effectively cosine of omega t, up to some phase shifts as determined by your normalization constant and your initial conditions. So this is how we actually solve a partial differential equation. The wave equation in particular separates easily into these two ordinary differential equations, which have solutions that you can go and look up pretty much anywhere you want. Finding the actual value of the constants that match this general solution to the specific circumstances you're concerned with can be a little tricky, but in the case of the wave equation, if what you want is, say, a traveling wave solution, you can find it. There are appropriate constants that produce traveling waves in this expression. So, to check your understanding, what I'd like you to do is go through that exercise again, performing separation of variables to convert this equation into, again, two ordinary differential equations. This equation is called the heat equation, and it's related to the diffusion of heat throughout a material. If you have, say, a hot spot and you want to know how that hot spot will spread out with time. Since this is a quantum mechanics course, let's move on to the time-dependent Schrodinger equation. This is the full Schrodinger equation in all of its glory, except I've just written it in terms of the Hamiltonian operator now. H hat is the Hamiltonian. The Hamiltonian is related to the total energy. I evidently can't spell total energy of the system. Meaning it's, kinetic energy plus potential. And we have a kinetic energy operator, And we have, well, we will soon have a potential energy operator. What h hat actually looks like is it's the kinetic energy operator, which, if you recall correctly, is minus h bar squared over 2m times the second derivative with respect to position. And the potential energy operator is just going, it looks a lot like the position operator. It's just multiplying by some potential function, which here I'll consider to be a function of x. Now this is an operator, which means it acts on something, so I need to substitute in a wave function here. And when you do that in the context of the Schrodinger equation, you end up with the form that we've seen before. I h bar d psi dt equals minus h bar squared over 2m d squared psi dx squared plus v of x psi. So that's our Schrodinger equation. How can we apply separation of variables to this? Well, we make the same sort of guess as we made before. Namely, psi is going to be xt, where big X is a function of position and big T is a function of time. If I substitute psi equals xt into this equation, you get pretty much what you would expect. I h bar. Now when I substitute xt in here, big X, big T, big X is a function only of position, so I don't need to worry about the time derivative acting on big X. So I can pull big X out, and what I'm left with then is a time derivative of big T. This is then going to be equal to minus h bar squared over 2m times the same thing. When I substitute xt in here, the second derivative with respect to position is not going to act on the time part. So I can pull the time part out. T, second derivative of big X with respect to position. And substituting in xt here doesn't really do anything. There's no derivatives here, so this is not a particularly interesting term. So we're getting vxt. All right. Now the next step in separation of variables is to divide through by your solution, xt, assuming it's not 0, that's okay. And you end up with I h bar 1 over big X, 1 over big T, canceling out the X, and you're just left with big T, 1 over T, partial of T dt. And then on the right-hand side, we have minus h bar over 2m, h bar squared over 2m, 1 over big X, second partial of X with respect to position, plus V. X and T are fully canceled out in this term. Now, as before, this is a function of time only, and this is a function of space only, which means both of these functions have to be constant. And in this case, the constant we're going to use is E. And you'll see why once we get into talking about the energy in the context of the wave function. So we have our two equations. One, I h bar over t, first partial derivative of big T with respect to time, is equal to E. And on the right-hand side, from the right-hand side, we get minus h bar squared over 2m, 1 over big X, second partial of big X, with respect to position, plus V is equal to the energy. So these are our two equations. Now I've written these with partial derivatives, but since, as I said before, these functions big T and big X are only functions of a single variable, there's effectively no reason to use partial derivative symbols. I could use d's instead of partials. Essentially, there's no difference if you only have a function of a single variable, whether you take the partial derivative or the total derivative. So, let's take these equations one by one. The first one, the time part. This we can simplify by multiplying through by big T, as before, and you end up with I h bar d big T dt equals E times T. taking the derivative of something and getting it back multiplied by a constant, again, should suggest two exponentials. Let me move this IH bar to the other side. So we would have divided by IH bar. And 1 divided by I is minus I. So I'm going to erase this from here and say minus I in the numerator. So first derivative with respect to time of our function gives us our function back with this out front. Immediately this suggests exponentials, and indeed our general solution to this equation is some normalization constant times e to the minus I e over h bar times time. So if we know what this separation constant capital E is, we know the time part of the evolution of our wave function. This is good. What this tells us is that our time evolution is actually quite simple. It's in principle a complex number. T is, in principle, a complex number. It has constant magnitude. Time evolving this doesn't change the absolute value of capital T. And essentially it's just rotating about the origin in the complex plane. So if this is my complex plane, real axis, imaginary axis, wherever capital T starts, as time evolves, it just rotates around and around and around and around in the complex plane. So the time evolution that we'll be working with for the most part in quantum mechanics is quite simple. The space part of this equation is a little more complicated. All I'm going to be able to do now is rearrange it a little bit by multiplying through by capital X, just to get things on top, and change the order of terms a little bit to make it a little more recognizable. Minus h bar squared over 2m, second derivative of capital X with respect to position, plus v times capital X is equal to e times capital X. And this is all the better we can do. We can't solve this equation because we don't know what v is yet. V is where the physics enters this equation and where the wave function from one scenario differs from the wave function for another scenario. Essentially, the potential is where you encode the environment into the Schrodinger equation. Now, if you remember back a ways, when we were talking about the Schrodinger equation on the very first slide of this lecture, what we had was the Hamiltonian operator acting on the wave function. And this is that same Hamiltonian. This is h hat, not acting on psi now, just acting on x. So you can also express the Schrodinger equation as h times x equals e times x. The Hamiltonian operator acting on your spatial part is the energy of, is the separation constant e, which is related to the energy, times the spatial part. So this is another expression of the Schrodinger equation. This equation itself is called the time-independent Schrodinger equation, or TISE if I ever use that abbreviation. And this is really the hard part of any quantum mechanics problem. To summarize what we've said so far, starting with the Schrodinger equation, which is this: time derivatives with complex parts in terms of Hamiltonians and wave functions gives you this, substituting in the actual definition of the Hamiltonian, including a potential v. And applying separation of variables gets us this pair of ordinary differential equations. The time part here gave us numbers that just basically spun around in the complex plane. Not the imaginary part. This is traditionally the real part, and this is the imaginary part. So the time evolution is basically rotation in the complex plane. And the spatial part, well, we have to solve this equation being the time-independent Schrodinger equation. We have to solve this for a given potential. The last comment I want to make in this lecture is a comment about notation. My notation is admittedly sloppy, and if you read through the chapter, Griffiths calls my notation sloppy. In Griffiths, since it has the luxury of being a book and not the handicap of having my messy handwriting, they use capital psi to denote the function of x and time. And when they do separation of variables, they re-express this as lowercase psi as a function of position and lowercase phi as a function of time. So for this, I used capital X. Sorry, I should put things in the same order. I used capital T of t and capital X of x, because I have a better time distinguishing my capital letters from my lowercase letters than trying to, well, you saw how long it took me to write that symbol. I'm not very good at writing capital psis. There is a lot of sloppiness in the notation in quantum mechanics, namely because, oops, geez, I have two functions of time. This is Griffith's function of position. Sorry about that. This here and this here, these are really the interesting parts, the functions of position, the solutions to the time-independent Schrodinger equation. What that gives us, well, what that means is that a lot of people are sloppy with what they call the wave function. This is the wave function. This is the spatial part, or the solution to the time-independent Schrodinger equation. This is not the wave function. But, I mean, I've already made this sloppy mistake a couple of times in problems that I've given to you guys in class. Namely, I'll ignore the time domain part and just focus on the spatial part, since that's the only interesting part. So, perhaps that's my mistake. Perhaps I need to relearn my handwriting. But at any rate, be aware that sometimes I, or perhaps even Griffiths, or whoever you are talking to, will use the term the wave function when they don't actually intend to include the time dependence. And the time dependence is, in some sense, easy to add on because it's just this rotation in complex number space. But hopefully things will be clear from the context what is actually meant by the wave function. What that tells you, though, in the end, is the trajectory of the particle. If you launch it as a function of time, tick, 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 as a projectile moves through the air in, say, x, y space. Partial differential equations, on the other hand, PDEs, you have several independent variables. So where in an ordinary differential equation we only had time, and everything was a function of time, in a partial differential equation, what you're trying to solve for will have several independent variables. For example, the electric field, the vector electric field in particular, as a function of x, y, and z. We're going to move now into actually solving the Schrodinger equation. This is really the main meat of quantum mechanics. And in order to start tackling the Schrodinger equation, we need to know a little bit about how equations like the Schrodinger equation are solved in general. One of those solution techniques is separation of variables, and that's the solution technique that we're going to be applying repeatedly to the Schrodinger equation. First of all, though, let's talk a little bit about ordinary and partial differential equations. The Schrodinger equation is a partial differential equation, which means it's a good deal more difficult than an ordinary differential equation. But what does that actually mean? First of all, let's talk about ordinary differential equations. What an ordinary differential equation tells you is how specific coordinates change with time. At least that's most applications. So you have something like x as a function of time, y as a function of time, sorry, not y as a function of x, y as a function of time, z as a function of time. For example, the position of a projectile moving through the air could be determined by three functions, x, y, and z. If you're only working in 2 dimensions, for instance, let me drop the z, but we might have a velocity as well, say vx of t and vy of t. These four coordinates, position in 2 dimensions and velocity in 2 dimensions, fully specifies the state of a projectile moving in 2 dimensions. What an ordinary differential equation might look like to govern the motion of this projectile would be something like the following. dx dt is vx, dy dt is vy. Nothing terribly shocking there. The position coordinates change at a rate of change given by the velocity, while the velocities change, dvx dt, is given by, let's say, minus kvx, and dvy dt is minus kv subscript y now, kvy minus g. This tells you that, well, where I got these equations, this is effectively damped frictional motion in the plane xy, where gravity is pulling you down. So in the absence of any velocity, gravity leads to an acceleration in the negative y direction, and the rest of this system evolves accordingly. The electric field has a value, both a magnitude and a direction, at every point in space, so x, y, and z potentially vary over the entire universe. Now you know how, excuse me, you know a few equations that pertain to the electric field that maybe you could use to solve to determine what the electric field is. One of these is Gauss's law, which we usually give an integral form. The integral of the electric field dotted with an area vector over a closed surface is equal to the charge enclosed by that surface over epsilon naught. Now hopefully you also know there is a differential form for Gauss's law, and it usually is written like this. This upside down delta is read as